This is where we were in our last video. We want to work this out using direct line integration and then using Green's theorem. We'll look at it using direct line integration for now. Alright? Now, let's use up the space that we have up here. I'm going to erase what we had written before. We know that we have limited space. Oh, I don't want to erase the Green's theorem formula. Let it remain there. Alright? Alright, so let's bring all of this up some more. Alright, now I'm going to use direct line integration. Oh, one thing I didn't do, I put this function which represents the vector field that the integration would be taking place in. But what about the curve? Right. You need to know the curve around which the integration will take place. Now, here for the curve, you will go, it's a triangle around a triangle anti-clockwise. Alright. Now the vertices are 0, 0, should be the origin to 1, 0, and then to 1, 2, and of course back to 1, 0, right? So let's do a little sketch of that shape. If we have our x and y axis, let's put our x and y axis. This triangle would be from 0, 0 to, let me draw straight lines. It would go here. What I'll do, let me draw the axes in thinner lines, x and y axis, alright, and then think the triangle would look more like this. So it goes here, then back here. So this would be 0, this would be 1, and up here would be 2. 2 would go across like this. Alright. Now, from 0 to 1, let's call this C1. From 1 to 2, let's call it C2. And from 2 back to 0, let's call it C3. Right? We're going to use direct line integration to do it. Now, let's repeat the function 2x plus y dx. So the integral of 2x plus y dx plus 3x minus 2y dy. 3x minus 2y dy. Alright. Now here, you wouldn't really be able to do an integration with x and y and dx and dy. We could have everything in x and dx alone. We could also have everything in y and dy alone. Right? However, what I notice is that it seems to be somewhat standard to use a parameter, a third variable, and they usually use t for the parameter. So let's do that. Now, going along C1 from x equals 0 to x equal 1. So you see from here to here, right? Now this is what you would do if you are asked in an exam to do this using direct line integration. But as I said in a previous video, probably it's just Green's theorem that you would be asked. But it's good to know both method, alright? Now, let's use a parameter so that if we use a t, we'd have everything in t alone dt. Okay? So let x equal t, so that in this case, x cannot be t, because guess what? You notice what happened? No man, y cannot be t. Y doesn't change, it's x. Alright, a mistake. Let x equal t, because x changes. Right? So let x be some variable t. You wouldn't have to use the parameter, you know. For practice, you could do it again. And let x equal whatever it is that you want to equate it to. Right? X would be equal to just x itself, and y would be 0 in this case, because you're moving along the x-axis when you go along C1. But we're using the parameter t because it seems to be somewhat standard, and if you continue studying this topic, wherever you go to do it, since it seems standard to use parameter, you might be asked to do that, and then of course you would already be accustomed to using parameters. So x equal t. Alright, what is y? Well, in this case y equals 0, because y equals 0 everywhere along the x-axis. Alright, you want to change dx to dt. If x is t, then dx by dt equals what? 1. So therefore dx is equal to dt. Alright, so dx is dt. So when you're writing it out, you can just change this to dt. You can just change this to t. This to t. Now, here, what is dy? Now, look at dx first. If you change x, and you say x is t, you're changing t. So dx and dt are the same thing, because you say x is t. But what happened to dy now? What happened to dy? Dy means a change in y now. But in order for y to change, you'd have to go up or down. Even if it's a small amount up or down. But what happened? There is absolutely no change in y as you go along x. So dy is equal to 0. Alright. So let's put these in. You are integrating this along t. Now here, what you have is that you have the integral from x equals 0 to x equals 1, but x is t, so it's from t equals 0 to t equals 1 of what? 2x, which is 2t plus y, but y is 0, it's plus 0, dx, but we said dx equals dt, right? Plus And then here you have 3x, which is t, x is t, minus 2 times y, but y is 0. dy, which is 0. dy. Oh, dy is 0. I wrote 0 already. dy. So this is gone. So what you have is the integral from 0 to 1 of 2t. Oh, dt. dx should be dt. Which is equal to 2, dt. Right, which is equal to 2 times t squared over 2 from 0 to 1, which would be 2 would cancel 2, so it's 1 squared minus 0 squared, which is just 1. Alright? Now you see the x equal t, you didn't have to do that, you know. I just want you to become familiar with using the parameters from now. You didn't have to do it. You could just have the integral from x equals 0 to 1 of 2x dx. Y would be 0, dy would be 0. So the same thing would happen. Right? But I want you to get used to changing into parameters from now. Alright, so that's what happened along C1. Let's see what happened along C2. Now along C2, you go straight up. Right? So here, if you want to use parameters now, what is x? X equal, what is y equal to? What is dx? Oh, and dy. We want to find both, all of them, and write them with the same thing. Again, you could just change, you could just write everything in terms of y and dy. Right? But let's use a parameter. Now what happened? When you go straight up above 1, x is 1. So x is 1. X doesn't change, it remains 1. Right? Y changes, so we could say y is equal to t. Right? Now, what is dx equal to? What's the change in x? In order for x to change, you'd have to go make some shift at right or left. But there was no shift into the right or left. It goes straight up. So dx is 0. What is dy? Well, if you find dy by dt, you get 1. So therefore dy is equal to 1 times dt. So dy equals dt. Alright? And now, I seem to have run out of scrolling space already. And now, let's change up the values. We're integrating. We're going from y equals 0 to y equals 2. But we said y is t, and we want to use parameters. So we're integrating from t equals 0 to t equals 2 of, alright, 2x. What is 2x? X is 1, so 2 times 1, see that? Plus y. What is y? Y is t, so it's plus t. Then we have dx. What is dx? 0 times 0. Alright? Plus, and remember, I could have a bracket here to show that the integral applies to everything. Alright? Remember, it's not just 2x plus y dx alone being integrated, it's everything. Alright, so 3x. So, plus 3 times x but x is 1, minus 2y minus 2, but y is t. I want everything in terms of t. And then dy, but dy is dt. Alright, so that's what we have here. Now, being that we run out of scrolling space, let's continue working upwards like this. Alright, let's use another color to show the continuation. So we have, alright, integral from 0 to 2 of 2 plus t times 0, but when you multiply by 0, all of this is gone. This will go. So it's 0, right? I didn't really have to write it. Plus, then you have 313 minus 2t dt equal, when you integrate this, you're going to, with respect to t, you have 3t minus 2t squared over 2 going from 0 to 2. Alright, so we continue. So 3t minus t squared, because 2 will cancel 2. 3t minus t squared. So we have 3t minus t squared from 0 to 2. From 0 to 2 equals, so 2 first, 3 times 2 minus 2 squared minus 0 after that, 3 times 0 minus 0 squared. All of this will be 0. So you have 3, 2, 6 minus 4, which is 2. So you get 2 for that part. Now, what we want to go is along C3. Now let's go along C3. What would be the equation of that line? Remember, the equation of a line is y equal mx plus c. C will be the y-intercept, and c is 0, so it's plus 0. So there's no value here for c. So it's y equal mx. What's the gradient? Rise over run is, the gradient is 2. So this line is y equals 2x. Alright, so along C3, y equals 2x. Alright? Now, as I said before, you could write everything in terms of x alone, dx, or y alone, dy. But I want you to get accustomed to using a parameter. So, parameter, let me write that first. Parameter t. Let x be equal to t, so that y is equal to 2t. Alright? So we have x and y. Now, what is dx? Well, we have x equal t, so dx by dt is equal to 1. So dx is equal to dt. You can see it from here. What is dy equal to? If you differentiate this, dy by dt, alright, by dx by dt would be equal to 2. So dy would be 2 dt. Alright? So you have that. So now, let's write down everything. We have the integral Now the integral takes place. We're going, okay, t, what is t? T is x. So we're going from t equal 1 to t equal 0. If you wrote everything as x dx, it would be from x equal 1 to x equal 0. But x is t, so it's t equal 1 to t equal 0. So we integrate from 1 to 0 of, alright, I have 2x plus y, in this case 2t plus y, which is 2t, and dx is dt, so we have dt, right? Just looking for uniformity, plus, and then we have 3x minus 2y. What is x? 3, x is t, t minus 2 times y is 2t times 2t dy, but dy is 2 dt, 2 dt. Okay? You could try doing it again without a parameter. What you would get is 2x plus 2x dx. If you write everything in terms of dx, right, and then 3x minus 2 times 2x times 2 dx, that's what you would get, right? But we're using a parameter here. So what we have is the integral from 1 to 0 of 2t plus 2t is 4t dt plus 3t minus 2 is 4t would be negative 3 minus 4. It would be negative 1t times 2 dt. So what we have is the integral from 1 to 0 of 4t dt minus 2t dt. Right. But when we subtract them, what we get is the integral from 1 to 0 of 4t minus 2t, 4t dt minus 2t dt would be 2t dt. So when we integrate that, we have 2t squared over 2 from 1 to 0, which would be 2, well, 2 cancels 2, so we don't have to worry about it 2 again. It would be 0 squared minus 1 squared, right? So it would be negative 1. Okay, nice. So now, to find the integral, let's give it a label. Let's call this int equals, because we can't be bothered to write all over again. So int is equal to c1 plus c2 plus c3. We go around the curve. So along c1 was 1, so is equal to 1 plus, and then along c2 it was 2, so plus 2 plus negative 1. So the answer you get is 2. Alright. Good. Now, in the next video, we're going to do it again, but we'll use Green's theorem this time. So I'll see you.